Here we have a linkage system with a rotating crank over here at A and a slider mechanism like a piston located here at C and a connecting rod between them that we'd like to analyze. And we're working with linkage systems. The first thing we like to look for is constrained motion. And for this system, we have two forms of constrained motion. Point B is connected by a rigid link, and it's forced to move in uniform circular motion. So for constrained motion, we can say that link AB is undergoing uniform circular motion. As such, we'd expect its velocity at the end to be r omega, and the accelerations to be r alpha plus r omega squared types. That would be a tangential acceleration, and that would be a centripetal type acceleration. So identifying point B as undergoing uniform circular motion helps us to understand the types of velocities and accelerations it can experience. The second constrained motion is straight line or linear motion, where end C undergoes linear motion in the x direction only. And as such, it'll have a velocity in the x direction only, and it'll have a linear type acceleration in the x direction only as well. Once we've identified the constrained motions, we then look for onboard relative motion events. And link BC provides that. If we look at link BC, the velocity of B with respect to C tells us that if we're located at C, that's the observer, point B can only undergo uniform circular motion about C. That would be an R omega type, where that would be B with respect to C, and any accelerations that we would expect to see would be R omega squared and R alpha types as well, which would show up here as an A tangential and show up here as an A centripetal acting directly along link BC, which is making a 20-degree angle. So identify constrained motions, uniform circular motion in the case of the link BA and linear motion here, and then look at the links themselves and realize that point B must undergo a form of UCM around point C. It has no choice since the length of BC can't change. Now that we understand the types of motion, we can solve this. So the velocity of B would be R AB omega, which would be 10 inches, and we're being told that omega A is 10 radians per second counterclockwise here as shown. This will be 10, and that will give us 100 inches per second. And it will act perpendicular to the link right there. So there's the velocity of B. And we can trace our angles up to here. If that's 40, this is 40, and this will be 50 right there. Now we'll apply step 2, relative motion of link BC. We can say the velocity of B, which we know, is the velocity of C plus the velocity of B with respect to C. And I like to sketch this out graphically here at first. So the velocity of B is right here. It's 100 inches per second, and it makes an angle of 50 degrees. And that's going to equal the velocity at C, which I don't know its value, but I do know that it has to be straight line motion. So it's going to look like that, plus the velocity of B with respect to C. We're on point C looking at B. So let me just lightly draw the link in here. So that's C, and that's B. And the velocity of B with respect to C must be perpendicular to that. So we know it's going to act something like that. And if we can bring in these angles, that's 20 degrees, which means that's 20. And since that's a 90, that makes this 70 degrees. So there I have a rough sketch showing the approximate directions. I know directions, but I don't know the magnitudes. So next we'll make a vector sketch of this. I always make a big dot where I'm starting. I'll call that point O. And we'll show at 50 degrees, there's our 150 degrees, and that's the velocity of B. And then that should equal these two vectors added, tip to tail. So the velocity of C has to be flat. Although I don't know which direction it is, it could be that way or this way. And then added to it is the velocity of B, which must act in this direction. So somehow I have to be able to add the velocity of C to the velocity of B with respect to C to get back to here. If we can see, there's only one way that that will happen. So the velocity of C must be here, and the velocity of B with respect to C must be there. And we know most of these angles. The velocity of B with respect to C is here. It makes an angle of 70 with the horizontal, so that's 70. We know this one is 50 over here, and that'll make this top one 60 degrees at this point. And we know that magnitude. So the law of sines will allow us to solve those two velocities. So we'll have 100 divided by the sine of 70 will equal the velocity of C divided by the sine of 60, which will equal the velocity of B with respect to C divided by the sine of 50. And with that, we can quickly solve for VC and VB with respect to C. So we find that the velocity of C is in this direction, and it's equal to 92 inches per second. And the velocity of B with respect to C turns out to be 81.5 inches per second. You could also do this with some of the Vx's and some of the Vy's and do it all by components if you like. There's nothing wrong with that. I like to make the vector sketches, I think. It's a little bit easier. Next, from here, we can actually find omega of the link itself. So this link is rotating, and we found the velocity of B with respect to C as up at this instant, which means it's got an omega of BC that we can find, and the velocity of B with respect to C is equal to R, B with respect to C, omega. So omega is equal to V over R, which will be 81.5 over 20 inches. So we find the omega of BC to be 4.1 radians per second, and it'll be clockwise. If we look at our link, we see that this point is moving with that velocity B up here. And this point is moving with some velocity of C at that instant, and it's also rotating as well, which we can see as this moves further up and this moves in is definitely what's going on. Now you may recall in some of our discussions on piston systems, we used the unit circle of radius r, and we showed that there's a velocity v. And if it was connected to a piston that was moving, we looked at the Vx values of that moving piston being related directly to the speed of the rotator. And let's look if that's true in this case. This is 40 degrees, which makes this 50 up here we saw, and that was 100. So Vx will be of B, will be 100 cosine of 50, which is 64.3 inches per second. And we found the velocity of c to be 92. Why does that have so much error? Well, when we do that model for a slider connected to a rotator, we make the assumption that the link, the connecting rod, is incredibly long. Ideally, it's infinitely long, but we want it to be long. And if it's long enough, the length of the connecting rod and the x-axis are close enough that we can say they're about the same, in which case this becomes true. And we approximate that solution. However, in our case, this link is 10 inches and this one's 20 inches. So these are not extremely long, and this is going to be quite different than that. And therefore, the y velocity here is contributing to some of this speed in the x direction. So when we say that the velocity in the x translates to a slider, it only does so under very extreme conditions of infinitely long connecting rods. For shorter connecting rods, we actually have to do the vector analysis. If we take a look at the accelerations, we will follow the same two steps. We'll identify constrained motion, in which case we have UCM here. So I expect to see a tangential and a centripetal. And here we have straight line motion, so I expect to see a linear type acceleration from there. And we're told that the omega is a constant of A, so the tangential is 0. We do have a centripetal acceleration. This is traveling in a circle, and as such, we do have an A sub c pointing towards the center. So let's start there. So the centripetal acceleration of point B will be simply r omega squared. The length of the link is 10 inches. The omega is 10 radians per second squared, and we'll get 1,000 inches per second squared. And it will point straight at A from B. And that's as much as we know right now. So step 2, write the onboard relative motion for link BC. So for link BC, we can say the acceleration of B, which we know, is equal to the acceleration of C plus the acceleration of B with respect to C. And this is done vectorially also. And again, let me make a small sketch here. So we have the centripetal of 1,000, and it has an angle of 40 at the bottom here, which makes it 50 up there. The acceleration of C, I don't know its value, but I do know that it has to be in the x direction only. That's one of our constrained straight line motion. Plus the acceleration of B with respect to C. That's relative uniform circular motion. So let me draw the link here very lightly. So we have point C and point B. And we know this is an angle of 20. And we don't know what these magnitudes are, or even if they exist, but there's the potential for an R alpha type, which I'll just call R alpha for now. It's the only one we have here. And for an R omega squared. And we know omega for the link BC, we found it, so this we actually know. The radius is 20 inches times 4.1 squared, which gives us 332 inches per second squared, pointing directly at C. If we translate some of these angles up, if that's 20, this is 70, which makes that 20 inside of here. And that'll help us when we do our vector sketch. Now the vector sketch is tricky because we have a lot of terms here. We have 1, 2, 3, 4 vectors to connect, where this one vector equals all 3 of these. And we have 2 unknowns. We don't know the magnitude of C, and we don't know the magnitude of the R alpha value. Let's see what that looks like. I'll pick a starting point here. And I'll show B. And I'll try to draw it roughly to scale here. So that's 1,000. And we know it makes an angle of 50. So we know we're going to add these other vectors, and they've got to take us back to where this one ends. Right? Adding these tip to tail is equal to that. Let's start with one of the ones that we know, which is this one. That'll make it a little bit easier. So at 20 degrees below the horizontal, I'm going to go 332, so I'll make it roughly a third of this size. So that'll take me about to here. So there's 332 at an angle of 20 degrees. And we don't know R alpha, but we do know that it will be perpendicular to that centripetal acceleration. So it needs to be in that direction. And I think you can see going in that direction is not going to help us. We need to end up down here. And now we can add A sub C to it. And we know A sub C is going to be in the X direction only. So if we extend that line out, they intersect right here, which tells us our values. So this right here would be the R alpha. And then this vector here, again, tip to tail, would be the acceleration of the piston C. And we know these angles. We look up here, this is 70 degrees from the vertical, which will make that 20, which plus 90 will make this 110 degrees inside of here, which will make that 20 degrees. This angle right here was 20 degrees. And with that, we can solve this. And the general format is to, at this point, since we can't make a triangle out of it, we're going to box this in. And we're going to write out the X equations and the Y equations. And we're going to do this as absolute values. So we can look at this and say this leg here has to equal this vertical leg plus that vertical leg. So that's 1,000. This will be the Y direction. We can say that 1,000. And if this is 50, this is also 50 right here. So 1,000 cosine of 50 has to equal 332 sine of 20 plus R alpha. And if that's 70, this is 20, that would be cosine 20. And from that, we'll find R alpha as 563 inches per second squared, and R is 20 inches, so there we can get alpha of BC as A tangential over R, which will be 563 over 20, and we find it's 28.2 radians per second squared. And for direction, we found this was down. So look at our link up here. This is down, our alpha. And therefore, that's the direction of alpha at that instant. So that's going to be counterclockwise for that. In the x direction, we have this leg right here, which is 1,000 sine of 50, plus this leg over here, which is 332 cos of 20, has to equal this leg down here plus this leg. A sub c is simple enough, plus the R alpha here, which we found, R alpha is 563. That's R alpha. And the horizontal would be sine of 20. And from here, we'll find the acceleration of point C is 885 inches per second squared, and it's in this direction as shown, so it's in the negative x direction. Another interesting way to look at this graphically is by the method of instantaneous centers of velocity, where we recognize the constrained motion, which forces the velocity of B to be in that direction, and the constrained motion of C gives us a velocity in this direction. If we extend out lines that are perpendicular to those two velocities, they'll cross at a region that we'd call C prime, which is the instantaneous center of velocity. And for that one instant, this appears as if it was a solid link moving with pure rotation around C prime with some omega. And that omega would be omega of BC, the same as we found before. And this would be like points on a wheel. And all points move perpendicular to these lines. So at any given moment in time, there's an instantaneous center of velocity that we could analyze and use it to find the motion and the omega. Now, the geometry to do that usually isn't worth the trouble, but it's an interesting point to find. It's important to note that this is not valid for any accelerations. It only works to identify the velocities and the rotational value for the link itself. And keep in mind, over time, this will move. Later on, when the link is over here, this will be down here. So we're going to see that this point is going to move over time. Here's a true 4-bar linkage where we have 1, 2, and 3 links, and the ground is considered a link. And if we have an input, let's say over here, the omega of B, call that B and A, it'll drive these links around and we'll end up with some omega of A, and maybe this has no alpha. This link might have an alpha. We'd have to check that along with this linkage. If we want to try the method of instantaneous centers here, we would extend the line out, again perpendicular, and a second line out that's perpendicular. And right here would be our instantaneous center, C prime, where link AB is rotating about that point as if it was a solid object pinned here. Now, it's only true for any given instant, but it would be a way, if we could find these lengths, to determine one velocity with respect to the other. This would be our ground link. That can't stretch or change. And for an omega here, call this A and B. This will have some corresponding omega B down here associated with it. Want to look for an instantaneous center. That's that velocity. There's that velocity. And extend them back. So that would be our instantaneous center at that moment in time, as this arm rotates through like that. Here's a fascinating look at a 4-bar linkage in motion, the yellow dot represents the instantaneous center of velocity, and see how it's moving off to infinity and then back at a point between the two. Also notice the constrained motion of the two fixed ground links as circles. Here's an interesting look at a 4-bar link that involves a gear, which acts like a link and a slider. The outer link is making a sawing motion. And also notice the cycloid shape that it's tracing out. By changing the lengths of the links, these 4-bar linkages are often used in machinery to trace out complex patterns. And here we have a strider linkage, which is two 4-bar links connected. And the center rotator is moving at a constant rate. And notice that it's taking on a running pattern. And just for fun, here's a 4-bar linkage that includes gears. The goal here was to create straight line motion as the output, which historically was a challenge for many machine designers. So understanding 4-bar linkages opens up a world of design possibilities for machinery. Thanks for watching.